Hello, Mr. Eric, Mr. Ryan, how are you?
Good.
What's binary search tree? Can you tell me what's binary search tree? Yeah, binary search tree.
A tree with
Numbers, yes.
And on the left of the root, it's smaller, and on the right of the root, it's bigger.
Yeah. Okay, so the left tree, the nodes on the left tree are strictly smaller than the parent, and on the other side, the nodes on the right tree are strictly bigger than the parent. Which order gives the in order the list in order? If we travel the binary search tree, in which order, and do we get the list in order, the sequence in order?
Yeah.
Which order is it? I give a few.
order.
Sorry.
In order.
Well done, in order, which is 2, 3, 4. So it's what? This is no, this is left, this is right. So it's L and R. Okay, in order. Okay, and which order gives the reverse order? Gives the 4, 3, R and L. This is called reverse in order. Okay, yeah, reverse in order. Okay, so today's task is very simple. Given a binary search tree, we want to find out of n node. Yeah, n node. N node with one label 1 to n. Yeah, 1 to n. 1 to n, and we want the in order of this binary search tree gives the 1 to n. In sorted order. Okay, this is very important. So if there's one node, how many ways can we construct the binary search tree? If there's one node.
One.
It's just one, yeah? If it's two nodes.
Two.
Two, yeah? Like that. 1, 2, and what else?
T1.
2, 1. So 2 is the root, yeah? Yeah, 1. Right, 2. N is 1, you give the 1 order. N is 2, you have 2. And how about n equals 3?
Your leg is wet.
N equals 3, how many? Do you want to give us, draw a few? You two want to draw a few. Right, come on. Ryan, can you let, come on. Come on, you want to draw? I'll give you a pen. Come on, just imagine how many ways can you draw. Draw here. 1 n equals 3. N equals 3. Please, Ryan. You want to help Gaga? Yeah, okay.
Weird.
Okay. If you're not drawing, can you sit down? If you want to help Gaga, then, that's one way. That's good. What else? 1, 3, 2, and then, come on.
3, 1, 2.
Okay, can you draw it? Come on.
3, 1. Oh no. 2.
Okay, 1, 2, 1, 2, 3. Yeah, well done. This is hard to get. Okay, 1, 2, 3. Okay, 3. And any more? Any more? This is perfect. 1. Yeah.
Wait.
Yeah. Keep drawing. Yeah, 1 is in the middle. That's right.
1.
Yeah.
Okay, you're gonna do it.
Okay, 1.
I like.
You cannot have nothing smaller than 1, right? So 1, and then 2, and then where should you put the 3? No, we have this, right? No. This is not binary search tree because left is big. Yeah, go here. That's right.
I drew it.
Yeah, okay, you draw it. Another one. Do we have more? Do we have more? This is the same as this one. What do we have more? Keep thinking. Well done. Yes. 1, 2, 3. Okay. Yes. Okay. Go back sit. Yes. That's perfect. 1, 2, 3. 1, 2, 1, 2, 3, 4, 5. 5 times. Yes. So if I tell you that I can group these two belongs the same, and these two belongs to the same. I can group this and these two and this one. Can you tell me on what basis I group this?
The root.
The root, yes, because this is the root of 2. This is root of these 2 are root of 1, and these 2 are root of 3. Okay. Okay, that's it. Go back. No drawing lesson. Come on. Okay, that's it. Go back, sit down. Okay.
I have a pen lid.
So, and when n equals 3, we got a 5 answer, yes? 5. The answer equals 5. So how do we, I mean, do you have any idea how do we count?
We count using a counter.
Using a counter based on what? How do we count? How do we
With
count?
dynamic programming.
But yeah, with the dynamic programming, but you need to tell me how.
Memorization.
That,
Top down, bottom up.
yeah, but we need to find out the way to compute the value, okay? To compute based on the number of roots, yeah? Yeah? Okay. So if you know this, let's do
I'm
this.
still alive.
Ryan,
Give on.
Ryan, it's not funny.
This belongs.
Okay, can we focus now? Can we focus now? Okay, so let's define a g function, gn. G function.
Yeah.
Gn means the number of ways we can represent. Okay, this is not good. The number of ways we represent is the number of binary search tree, unique binary search tree with n nodes. Okay, this is the answer we are going to look for. Okay,
Yeah.
the answer we're going to look for. Okay, so now Gn is the number of unique binaries. This is the answer we're going to look for. Okay, so we define another function fin means that if there are n nodes and if we place the I as the root, okay? If we place the I as the root here, if there are n nodes, so can you tell me first question is how many nodes if I put the I in the root? How many nodes on the left hand side?
I minus 1.
Yeah, and how many nodes on the right hand side? Like if there are n nodes.
N minus I.
We're done. Okay.
Cool.
So fin is it equals to g
The
I
one that
minus
belongs
1
to the whiteboard.
and g n minus I. So is it plus or multiple?
Multiple.
Multiple, yes. Because look, these two are independent. Yeah, the combination should be multiplied together. So this is the function, and then gn. There are n nodes, and how many ways I can put the put a node? You know, how many possibilities can we choose to place the root node if there are n nodes? If there are 3 nodes, how many different ways we can put the root? Come on, that's an easy question.
5.
No, I mean the root. 3, yes. Okay, so look, this because each node can be chosen as the root, right? So this way we can say is what? f1n plus f2n plus fnn, right? Yeah? Yeah, simple?
Yeah.
So this one, we can use the mathematics symbol to simplify this. Look, yeah? This one, we can do it as this symbol. Look, remember we talked about this symbol. Yeah? Like a E, but the opposite of E. Alright? This one, yeah? Opposite of E. This one would be I equals 1 to n f I n. Right? So look, f1n plus f2n plus f3n plus tfnn equals this, yeah? Sum, this reads as sum of fin, where I is from I plus I equals 1 to n, right? Correct? So this is, look, if we use this one, substitute this to here, so what do we get? So we can just do this. So G,
you didn't rub out my balloon.
Gn equals sum of I equals 1 to n. Gi minus 1 times Gn minus I, okay? So this is the function we get, dynamic programming function. What's the G0? G0 equals what?
G0 equals
G0 and G1 equals what?
1.
Yeah, the base case is, look, G1 is 1, yeah? Okay, so look, these labels are from 1 to n. If I, yeah? Okay, can you, yeah? Okay, let's it go.
Ba, 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 ba,
Okay, so
ba,
Gn equals Gi minus 1. If we shift this n, right? Because if we label this as 0 to n minus 1, right? If we label it, and then this will be Gi and n minus I minus 1. Yeah, this is the same thing. Yeah, if we shifted this, okay, Gi times Gn minus I minus 1. Okay. So we can implement this function using dynamic programming. How many ways we can implement this? Come on. How many ways we can implement this function?
No. Wait.
How many ways we can implement the dynamic programming function? Two.
Button
What are those?
up.
Top down.
Button up.
Bottom up. Okay.
We're using cash on top down.
Okay. So look. Remember this Fn. What's this? Fn equals Fn minus 1 plus Fn minus 2. What's this? Can you tell me? F0 equals 0. F1 equals 1. Can you tell me what's this? Can you tell me what's this? Fibonacci number, yeah? So look, Fibonacci number. Let's say if I want to calculate F4, we need to know which two values. F3 and...
F2.
In order to calculate F3, we need to know which value.
F1 and F2.
F2 and F1, okay? Keep going. Look, so look at this F2 are calculated multiple times. So if we're using this top down, calculate top down, we need to use the top down, we use the recursion. But in order to avoid calculating this over and over again, what keyword should we give to the function? Come on, you just wrote it. You just wrote it.
What do you mean wrote it?
We need to give what keyword should we label the function?
Programming.
So we don't calculate this F2.
Minimization.
Yeah, minimization. And in this case, which keyword?
Graph.
Come on, it's there somewhere on the board. Come on. Cash, exactly. So you wrote it. That's why I say you wrote it. So F2 is once calculated, we save it. So next time, look, if F4, we want to calculate F4, we know F2. And then when we calculate F3, we need the F2 again. So do we need to calculate this F2 again?
No.
Because we already calculated here. So instead, we just look it up in a notebook, which is the cache. Yeah, let's define the cache. Yeah, you can implement the cache by yourself. In the function, you can check if n is in the notebook. Then if it's in the notebook, we just return the entry in the notebook. And before we return the function, we save the value in the notebook. Yeah, like Fn equals the notebook n equals Fn and return notebook n. Okay. And the bottom up, bottom up is what? We calculate F0 and then we calculate F1, and based on the previous two values, we calculate F2, F3, F4 until we reach Fn, right? Okay, so now let's implement this function.
Oh,
Come on.
you rubbed out my Catalan.
Yeah. Define. Okay, I'm going to. Okay, sorry.
I'll do
You
it.
put a cache. Okay, cache. Ryan, can you know?
You didn't rub out my balloon.
Okay, define. Yeah, let's write down. Define G n, right? So if n equal 0 or n equal 1, return what? What's the base case of value we just talked about?
The one.
Okay. Then we need to sum. Look, in Python we have this sum function, right? Sum function 1, 2, 3, 4. What does it return?
Return.
You can take it. Yeah, you can take as many parameters as one, and we can also supply it with a list. 1, 2, 3, 4. What does it give us?
5, 6.
What does it give us?
10.
10. It's the same. Okay. So now we want to sum. Return. Sum. Remember, Gi times G n minus I minus 1 for I in range n. Okay.
Yeah.
That's it. Yeah, that's it. You see, so simple. The most difficult part is that we analyze the problem and come up with this formula. Alright? Formula. What's the time complexity for this one?
n square.
Can you tell me what O(n) square is correct? Can you tell me what's O(n) square? How we get O(n) square?
I didn't say it.
But O(n) square is correct.
I didn't say it.
What did you say?
said it.
Yeah. Ryan, why is O(n) square?
Because that's
How many?
I know.
How?
4 loops and G.
Yeah, because we need to calculate n values. Yeah, g value. How many g values we calculate? There are n, right?
Yeah.
And for each one, we need to give a loop. So let's n gn squared n squared. What's the space complexity?
N.
Yeah, well done. Why? How many n values have we? How many?
G.
Sorry.
1.
On is correct. Why is it on? How many g values do we need to calculate?
1. 2. 1.
Why is 1? Sorry?
G. N.
N value, because we're using cache, we don't want to calculate the G0, G1, G2. We need to, at most, we will store the N value. That's why we call it Gn, okay? LON, right? Okay, now we do this bottom up, okay? Bottom up. Define, again, let's call it Gn, okay? For the bottom up, we need to store the values in the what? In the list, yeah. So let's call it let's just call it something full, okay? G equals.
What do you mean food?
Yeah, I just come up with the random number. 0 times
That's
n
food.
minus 1, right?
Not food.
What does this mean? What does this mean?
It means what it
What,
means.
everyone, what's this mean?
It means what
Number 0 times n plus 1. What's this mean? Eric, what's this mean?
It means that 0 times n plus 1 is 0.
No. This I talked about this before. Remember, this is the list of n plus 1 elements. So each one is 0. Yeah, that's the list. Yeah.
I meant that.
Yeah. Okay. So now the first one is G0 equals what? G0 equals what?
Oh.
G0 equals what?
G1.
G0 equals what? What value? What value are we giving it to?
1.
1, yes. Now we just need to iterate for I in range n plus 1, and then I is the number of nodes, yeah. And then for j in range I. So now we can say g j plus equals gi plus equals gj times g what? I minus j minus 1, okay? So it's a bit harder to understand it in this case. Yeah, because the loop, the first loop is the number of the nodes. And the second loop is saying that which is going to be the root, okay? Which is going to be the root.
Yeah.
So GI, the answer of GI would be equals to what? I place the GJ and then I place, this is the formula, okay? And then finally I return GN, right? This is the answer we're looking for. What's the time complexity if you're looking this for loop? Come on. How many for loops?
2.
So what's the time complexity?
O squared.
On squared. Yeah, it's roughly on squared divided 2 because the j, the second inner loop, j goes to up to n. It doesn't go to n, right? Go to the I, it doesn't go to the n. So it roughly n squared divided by 2. But I will drop the constant, okay? What's the space complexity here? Come on, it's very easy to. On. You see? So the bottom up, if we look at the code, the bottom up, we can easily see the space and time complexity, yeah? Because it's easier to understand. But for the top down, we are using recursion, so you need to think about it, right? But both solutions give the same time complexity and space complexity, okay? Yeah? Okay, so this is pretty much the today, but today we're going to talk about, actually this is a very interesting mathematical problem, and the answer is called Catalan. Look, this is new, okay? Catalan numbers. Catalan numbers.
I called them caterpillar.
So the Catalan numbers exactly is used. Is answer to this question and many other similar problems. Okay. So what's Catalan numbers? So Catalan numbers. Okay, let's call it G.
I feel so wet.
Gn equals what? Equals n plus 1 c2n. C
It might be rain.
2m. What's this c function? Remember? What's this function? C. What's this C? Combination, yeah? Alright, Ryan, listen to me.
Yeah.
What's this C function? Remember, we talked about the C and P, remember? Combination, permutation, C. If I want to pick 3 apples, I want to pick 2 apples out of 3 apples, how many ways? 2. Sorry? No.
1.
If I want, there are 3 apples, I want to pick 2 apples, how many ways?
3.
3, yeah. It's the same as 3, 1, right? It's the same as picking 1 apples out of 3. Because look, every time you pick 2 apples, you also have a solution for picking 1 apples, right? So this is C2n times n. Let's check this. If G3, okay, G3 is equals to 3 plus 1 and C 2 times 3 and 3, okay? So what's this answer? 4 times 1, C6, 3. What's this number? 6 times 5 times 4 and 3 times 2 times 1. And then we have a 4. Okay, so these cancel out. These cancel out. Look, what do we have now? Look, Eric, look. Come on.
Yeah.
What's the answer of this? G3 will be equals to 5. Look, we just cancel out everything except the 5. So this is the Catalan numbers, okay? Okay, n plus 1, C2 and n. And then it has the recursion depending on previous one. Gn plus 1 equals what? Equals the 2n plus 2 and 2n. Gn. I think it's it. I'm not sure. I have to check it out. I have to look it up. N plus 2 to n plus 1. N plus 2. Okay, sorry. N plus 2 to n plus 1. Okay. Okay. So that would be if we have this function, we let's implement it in next lesson. Okay. This is the Catalan numbers. Okay. Let's implement it in next lesson. It'll be quite interesting. Okay. So today we talk about the number of unique binary search trees given this n nodes. Okay. Yeah. Yeah. Have to pick the numbers. Okay. That's it for today. Good job.
Bye.
Bye.